Hi everyone, how's it going? Welcome to this week's Friday presentation. I have kind of an interesting thing this week. The thing I'm going to be presenting is actually called Griffin. It's the same spelling and everything. It's not a joke. It's towards a graph-centric relational database foundation model. So yeah, let's jump into this. Of course, my supervisors for this directed studies course are Prof. Ali Grabani and Dr. Xiyuan Zhang. So a little bit about me. I'm a PhD student here in the computer science faculty at UNB. I'm also a cybersecurity software developer at CIC. And as you know, I always start off my presentations with how I love nerdy things, and I don't think I'm ever going to get a nerdier thing than this. Reading this for the first time in the work was kind of hilarious, where they said, in this work we introduced Griffin, a graph-centric relational database foundation model. I went, I don't know, but we'll see. So the objectives for this introduction, for this presentation, are to go over the introduction, some overview, go through the methodology in the different sections of the paper, and then I'll kind of take any questions that people might have. So first and foremost, introduction. When we think about different kinds of data, we might understand that certain pieces of data have relationships between them. We might think about sentences and words between them, for example, like words will come after one another, they're kind of sequential. We might also think about images and kind of pixels in neighboring regions as being kind of this grid where the pixels are literally next to each other. And we might also think about data kind of like in a table, for example, like in Microsoft Excel, where each kind of row in this table is totally independent. It doesn't depend on any other thing. So we can use various techniques for this. We might use multilayer perceptrons. We might use LSTMs or CNNs to deal with these different kind of structures that we see within data. But what happens when, and again, these are all kind of special cases of graphs. And we might say like, I don't know about the MLP case or the unrelated case. Graphs need to have edges between the nodes, don't they? And technically, no. Technically, you can have a graph with no edges. As long as it has nodes, that's still perfectly fine. But we might say these are special cases of graphs. What happens in the real world when we come up to a graph that looks kind of without these assumptions, or it might change, where every kind of graph might be very different, where there isn't kind of this sequential or grid-like structure. Well, in these kind of cases, we might need to come up with a graph model that can actually process this and maybe do things with it. In this kind of setting, we have different kinds of tasks, not unlike if we're processing images or sentences, for example. We might think of like a graph level task. So if I give you an entire graph, can you tell me if it's malicious or if it's benign for doing kind of malware detection? I might also ask you about node level tasks. So for example, if we were playing like cops and robbers and there's this cops and robbers graph, if I just show you a node and its neighborhood, can you predict if that node is going to be a cop or a robber? We might also think about edges. So we're going to see how that comes to fruition in a moment. But we might think of if there is a relationship between people in a Facebook network, for example. So if I show you a person and their neighborhood, and I show you another person, can we actually predict if there's a relevant edge between them, maybe a yes or no kind of thing. So again, these neighborhoods might look like the following. This isn't the most straightforward thing when we think about images, especially for convolutional neural networks. We understand that we might be compressing the neighborhoods in on themselves repeatedly until we arrive at some final representation. But here we don't necessarily have that because it's not like a grid, it's not a nice structure. But we can still talk about the neighborhood of things that are around a given node. And we might use those other nodes and their relationships to actually construct not necessarily a unique representation, but a good approximation for how this node might differ with respect to all the other nodes that it belongs to. So here we can see kind of the top level where if we have some kind of target node A, we can see that the first order neighbors of B, C, and D are there, and as well as their kind of second order neighbors. And we also see that the A node might actually also reference itself later down in this kind of tree. So this is one way of thinking about it. I don't really prefer this. I much rather have this. So if we can play this little video, we can think about the neural network, the graph neural network, as passing messages between nodes to learn their representations. So if we can play it, we skip ahead a little bit.
The properties of fixed structure and ordering, we can similarly gain a better understanding of each node by aggregating the messages received from all neighboring nodes. Now, Hold on to your new message, Andy, as your friends complete their first round of message passing.
So here we can see every neighbor exchanges a message
Observe how
with
the
every other
color
neighbor.
of each message
And the
changes
messages will change
to
kind of over
represent the
time.
newly aggregated message. And with each new round of message passing, more and more information gets passed around in the graph. Over sufficient rounds of message passing, we will
So we do this
eventually
kind of sharing
obtain
process
a final
repeatedly with all of our
representation
neighbors.
of each node in the graph that will describe it given the larger context. Now, we can actually also view the rounds of message passing as a series of layers, just like in our convolutional neural network. Here, we go from the input to round 1 of message passing, and then round 2 of message passing.
So I'm going to stop it here, but again, the main takeaways are just that this is kind of like convolutional neural networks, except we might not be necessarily doing that max pooling and shrinking the information over time, but we are sharing the information with our neighbors repeatedly. So if we want to just think about it like that, that makes life a little easier. So okay, where does that take us next? So we have a better understanding of graph neural networks and how they might be used, the different kinds of tasks there are, and why, again, we're using them. But now let's bring this with respect to the things that we're going to be talking about today. And just before I start talking about the paper, our main focus, we're actually going to take a little detour. Because when I was doing my data mining course with Dr. Rusbay in my second semester, I interestingly got to look at this other paper called Grape. And I full-on reviewed this paper for the course, and this is a fundamental paper that is referenced by the paper I'm presenting today. So it's kind of funny how all of these things are occurring. I don't know what the odds of this are. Maybe the universe is trying to tell me something. But yeah, so here we can think about this thing called Grape, and it's going to be basically the one-dimensional or the one-table version of this higher order, more complex thing that we're going to talk about in a minute. And it handles this thing called handling missing data with graph representation learning. And this is just kind of a fancy way of saying we're going to be doing missing data imputation. So we're going to try and predict values if they're missing. So here we can go back to one of the things I said earlier, which is that we might have lots of these rows in a table and they might be unrelated. But that was actually flat out lie. I lied to you. I'm really sorry. I won't do it again. But the way I lied to you is very important because these are related. They are related through their features, right? Each sample is going to have maybe an X or Y or a Z. It could have like a name or some other kind of attribute. But we can relate all of these things together, where we might see that kind of the purple parts of the bar for this graph representing the dimensions, they might become their own nodes, and they might be distinct from all the other kind of samples. We might also represent the values between those two things on the edges themselves. So this forms a bipartite graph. So okay, how does this actually relate to a table? Because tables don't really look like graphs. But we can see that if we have all of the observations on the left-hand side and all the features on the right-hand side, we can see that we can represent missing values that we would normally have to put in the table as like NA or I forget what the NumPy value is. But we can represent those in the graph just by missing the edge. So that might be an edge prediction task that we have to complete after. So this is kind of the simplified version. This is the little more complex version where we might actually be predicting the values between these things in this kind of bipartite graph edge prediction problem, as opposed to how it was previously framed as kind of using just rows and tables in this single table kind of setup. So yeah, that's a little bit on Grape and how we can use graphs to restructure our problem and make predictions on a table. But now we're going to talk about this paper. It's called Griffin Towards a Graph-Centric Relational Database Foundation Model. And it's basically going to be this on top of what the other paper just was. So here we used like a table as well as a message passing neural network if you want to be very specific. But now we're going to upgrade this to be a relational database. And here we're going to use a transformer. And a good question would be like, why would we use a transformer? Like, why couldn't we just do this other thing and just scale up the graph neural networks forever and have everything magically work out? Unfortunately, that can't happen because most things we have in terms of techniques, they work well on single tables, but they don't work well on these kind of relational table settings. This is due to like structural complexity, a lack of processing pipelines, as well as unique computational patterns that occur within the relational databases themselves. So that's one piece of motivation. Another piece of motivation is that we have foundation models, or kind of like backbone models if you're a developer. And we use these models all the time. We use them, like, for example, in text. We might think about Llama. We use them for vision related tasks, like if we're using VGG. And the main point here is not that we want these things to necessarily do the thing. It's getting them to give us a representation of the thing we're working with so we can do some other task. So for example, if we're thinking about VGG or convolutional neural networks, we understand that we'll start with an image, and then at the very end we'll be given some vector that represents that in very high dimensional space. But that is the backbone model, right, or the foundation model. But what we do after with that, we might do classification, we might do segmentation, we might do all these other image-related tasks, but we can extend this to large language models if we wanted to do summarization-based tasks, right? So the key point is that we don't really have anything like this for relational databases right now. So that's something that the work wants to address. We basically just want to give you like a CNN or some kind of Llama model that you can just go and use on databases. That's the point. So in the work, looking at some of the methodology, we start with the relational database itself. So for example, we might have different kind of products in a table, different users, and they might all be related through these kind of key pairs. So like the foreign key and the primary key, if you remember back to your database course in undergrad. So this is good. And again, before we process this through the rest of our pipeline, we might want to do some kind of pre-processing on this data. So here, some key points are that any metadata about the database itself, so the table names or the column names, these are all going to be transformed into their respective kind of embeddings using a sentence transformer. We also apply quantile normalization to any kind of numerical data we see. We also perform column level time scaling on temporal data because some of these rows might come with temporal features, but when they were made or when they ended or something like that. We might also say just for regular text if we see that, so we might use a sentence embedding just to represent that. And then for categorical data, we are again going to use a sentence embedding. So lots of embeddings today, lots of sentences, and this has some quite nice properties and lets us get around some other tricky issues that we'll see later. So great, that's a little bit on the database that we're gonna just take in. We might also want to perform some kind of task. So here we can see, I can't really see my mouse very well. Here we can see this kind of missing value that we might want to estimate or impute. So we might say, given all of the data in my database across all of the different tables, how can I give a really good estimate of this value? So the first thing we're going to do is we're actually going to get a sample subgraph, where a rooted subgraph is what they talk about in the paper. Technically speaking, this is a heterogeneous temporal rooted subgraph. So we are going to first restrict the size of the subgraph based on its timestamp. So if we think about the relational database, we might literally, if we're trying to impute some kind of like cell in a table, we might look at its timestamp, and then we might mask out all of the values that occur after that time step. So we're only dealing with data that's come before it in order to predict it. We also do some other things. So we're going to have a cross-attention module as well as a message passing neural network module, so we can see those in green and blue respectively. And then most importantly, we also have a unified encoder model. So we're going to talk about this just now. So yeah, and then after, these are the different parts of the module architecture. So in more kind of specific detail, so we can see like that orange blob, it maps to the same orange blob on the other side, same with the green and the blue. But at the very start, we can see that there's going to be this kind of unified feature encoder, and it's going to have the sentence embedding encoder as well as the pre-trained numeric encoder. Forgive me, it's just kind of hard to see the slides. It's especially small on my screen. Yeah. So starting off, we might take a look at the cross-attention module, right, or the unified feature encoder right off the bat. This is really important because it means that anything that's coming to us, we're going to be able to represent it as an embedding. So if I have some label or some cell that says the word cat, then I don't have to think about how to make this into some one-hot encoding and do very kind of specific things with it. I can just run it through the sentence transformer, and then it will always give me a semantic representation for what that is. So that's really good. As well as for the pre-trained numeric encoder. So if there's some kind of value that's like really large, that's going to also be mapped to some kind of large embedding space. And this is interesting because I actually tried to work with, this is called kind of mixed data imputation. It's quite challenging without this kind of sentence transformer, sentence transformer approach. I actually tried this as part of my coursework, and the best I could come up with would be to like basically concatenate like an extra embedding or an extra encoding space for categorical features alongside one for numerical features, and then train the loss for both of them differently while like summing them. So we might have like the cross entropy loss for whatever extra bits would have been on the end here, as well as just the MSE loss or the L2 loss for the numeric representation over here. So yeah, and we can also see that we're going to push these embeddings through a cross-attention module. So if you're familiar with transformers and this notion of a query, a key, and a value, we can understand that it's going to basically be paying attention to all of the cells in a given table. So we're going to have like a given row, and then for all of the cells in that row, we're going to push it through the unified feature encoder first, and then we're going to perform cross-attention on it. So every cell of the row we're looking for is going to get to see the other important parts of the cell before it ships it off to a final vector. And of course, this is going to be trained and adjusted over time to meet whatever loss is happening. Some more important things are that the column features are actually going to be used to compose our keys. And the node representation and the task representation are going to be pushed through a multi-layer perceptron, which is going to help us form our query values. And then finally, we'll have our final vector that will be updated from our original node representation as well. So okay, after we have this, we might actually take a look at all of the other nodes that have been embedded in this similar way with cross-attention, and we might form its rooted subtree and start passing messages around. This is like very similar to what we were doing previously with Grape in kind of this one table setting, except now we're starting to aggregate it across multiple tables. So two things happen here. First, we pass messages across or within relation types first, and by relation type, I literally just mean like the single table. So messages are going to be passed in this rooted subtree within a single table first. And then once those representations are created, then we will start to, I don't know why that got cut off there, and then we'll start to combine them across the different tables themselves. So that's a little bit on the message passing neural network. And then after we do this, the message passing neural network will give us our final representation for the given missing value we're trying to impute or find. With respect to like all of the rest of the database and all of the rest of the relevant values. So yeah, that brings us to the final component of the Griffin architecture, where we have a unified task decoder. And here, depending on what we want to get back from this, we can either have, if it's a regression task, for example, if we're working with numerical data, we might use the pre-trained numeric decoder to actually get the missing value back. Or if it's kind of a classification task, we might need to pass it through the query candidate labels. I'm not sure what that is, but it's essentially the decoder for the classification task. And here this is quite interesting because the thing that we get back is going to be compared against all of the other embeddings for the given categories, not the categories themselves. So for example, if I have the word like cat and dog and bird, and those are the categories I'm trying to distinguish, we first are going to transform those through our entire architecture. We're going to transform those through our entire architecture, and at the very end, we're going to have some kind of vector that we are then going to compare against the vectorized versions of the cat, the dog, and the bird, respectively. And then we're going to take whichever one has the most cosine similarity. So that's how we're actually going to pick the correct label in the classification task. It's not that we're just going to check, does 1 equal 1? It's not quite that simple. And then afterwards, it outputs its final prediction for whatever the missing value might be. So I guess now that we have an understanding of the Griffin architecture, we're going to get into the experimental setup. So in the work, they consider 200 data sets, single table data sets, and these come from TP, Berta, and CART. And they contain things related to healthcare, social sciences, entertainment, marketing, media, finance, like all these very vast and different domains. Because again, the whole point of this work is to create a foundation model. So that in the same way, I can go just grab some CNN model with some pre-trained weights from maybe Hugging Face, do a little bit of fine tuning and have a really good model. Someone else can take this architecture as well as maybe some pre-trained weights and maybe do a little bit of fine tuning and also have a very good database foundation model or relational foundation model. And across all of these, it comprises roughly 10 million rows, which is great. So that was for the single tables. For the relational databases themselves, there's quite a variety from things looking at Airbnb to Amazon. But again, the main difference here is that these are kind of the multi-table databases, so they're not single table like the others. In terms of metrics, they use rank, accuracy, ROC, RMSE, MAE, and log loss. So lots of different metrics for us to compare across to see if maybe the model isn't performing well in this very specific one that we've chosen maybe. So that's a little bit on the metrics. The Griffin model itself, they state that it has a hidden dimension of 512. For the message passing neural network, it has 4 layers, and 2 layers are basically used to perform the uniform temporal sampling across all the relevant samples. They have a fan out of 20 samples per layer. So here I guess they just pick 20 random samples as good approximations from all of those that have been non-hierarchical or non-temporally masked. So that's good. For the sentence embedding, they choose the nomic embeddings. I've actually never heard of this before, and I guess they truncate it to 512 dimensions. And for the cross attention, they use 8 heads. They use dropout 0.1, and then they use an activation function. I haven't really seen used out in the wild yet. It's called SILU, so it's the sigmoid linear unit. So it kind of looks like ReLU, except it has just like a little bump right before it transitions up. In terms of the training pipeline, they do a couple things. So first and foremost, they train Griffin on this completion pre-training set. So here they only consider the single table values, and they use them to predict, I guess, just masked or completed things. So just like what we were doing in grade. And here we can see that there's this interesting looking loss function where we have 1 minus the cosine of two things fed to a model. So the first one is the model, or the Griffin model, and we can see that we're going to give it all of the cells for the row we're trying to impute without the actual row that we're trying to impute, and we're going to give that to the model. And then we're going to have the final encoded version for just the actual value we're trying to impute. So in that way, we might say it's going to be like the y predicted and then the y true. But we're just doing this with embeddings versus like actual class labels. So that's a little bit of what's happening. So they do this kind of pre-training on just the single tables starting out. Afterwards, they perform a joint supervised fine-tuning using all of the remaining relational databases and I guess some of the single tables as well. Here they use cross-entropy loss for the categorical or the kind of classification-based tasks, as well as L2 as the L2 norm for numerical or kind of regression tasks. And then lastly, after this, they use some downstream fine-tuning. So if you know exactly kind of what you might be trying to do, if it's only for regression or classification, then maybe you do a little bit more training just on that final task alone. So again, this is just all the setup that would go into giving you some model that you can do a little bit of fine-tuning on so that you can make predictions accurately using a database. So in their work, they also consider 3 different variants. They consider Griffin unpre-trained, Griffin pre-trained, and then Griffin relational database supervised fine-tuning. So they compare this model with existing GNNs that they use on the multi-table kind of setting or the relational database setting. So they use GraphSage, GAT, PNA, and HTT. For the single table setting, they use a multi-layer perceptron, DeepFM, FT-trans, and then XGB. And then they also, for all of these kind of methods, I guess they use deep feature synthesis. Not too sure what that is off the top of my head, so don't ask me. But I know that it improves basically the performance of all of these other models that are used on the single table setting, just so that it's actually kind of a fair comparison. The researchers have the following research questions. Can Griffin with its advanced design outperform existing models under the same training settings? That's the first one. Question 2 would be, can utilizing a single pre-trained checkpoint universally enhance predictive performance? And then the third one, can joint supervised fine-tuning with relational database improve transferability, and under what conditions does it provide the most benefit? All of these are important, especially the last one, because that's the thing that's actually going to prove that this is a foundation model, just different from some model I just trained in my basement, maybe on some hyper-specific task that will do very well. So that's something to keep in mind. In terms of results, we can see the following. So all of the things in green are the Griffin models, and we can see the difference between the unpre-trained and the pre-trained. With respect to rank, accuracy, all of the metrics, it performs much better, which is great. And we can see that in most cases, the pre-trained model performs a little bit better than the unpre-trained model, but it is kind of very telling that even without any pre-training, that this model is doing very well, even in comparison to all other methods. So that's great, but we also want to know, again, this is a foundation model, we want to know about its transferability. So the authors perform transferability analysis, and they consider two kind of main axioms. One is the similarity of what's happening, and then the other is diversity. So the main question is, like, if the database I know I'm going to be working on is going to be like a consumer database, I should probably train my Griffin model with like another consumer database, right? And presumably that would give me very good results. So that's one way of thinking about it, is like, are we going to be training this on specific or similarly representative databases? The other is diversity. So what happens if, again, I want to perform these tasks on an e-commerce data set? What happens if I don't consider a similar e-commerce data set? What happens if I consider like a health data set and like an air traffic control data set and I don't know, like an education data set, things that are very diverse and not necessarily related to the thing that I'm working on. So here, I guess I can see my pointer, yeah. So here they consider a commerce data set, and they see that when they use a supervised fine tuning on another commerce data set, that it does the best. So that's great. Similarity can do well. We also see on another data set, so this is a subset, a commerce subset, that interestingly that the others do well. So here we distinguish between commerce 1 and commerce 2, they're split, as well as the others, which is just a collection of other databases that might look at like social networks and things like that. But here we can see that when we do supervised fine-tuning with the others 2 version, that's going to do much better than if we just use the commerce 1. So that's interesting as well. And then we see no pre-training in this case does the best when we're just looking at like a very diverse set of databases, as well as the others 1 does well here. So that's pretty interesting. In terms of ablation, we can see that we might start to remove parts of the Griffin module. So here we can understand that if we remove the average attention mechanism in the rank kind of column, then suddenly we would have a huge amount of error. So that's like really important. We can also see, I guess that's the biggest one, but there are some kind of drops when we take the others out too. So we definitely want to keep those. And then I guess in terms of findings to answer the research questions, Griffin unpre-trained outperforms all models by significant margins, so that's really, really great. It means that you don't have to do all this pre-training if you don't want to. You can just go use it. Also, Griffin pre-trained with completion and joint supervised fine-tuning on single tabular data sets outperforms its non-pre-trained variant. So that's good. Just like what we saw earlier with the results, that pre-training, if you decide to do it, will give you a little bit of a boost. And then lastly, pre-training diversity is just as effective or better than pre-training on similar data sets. So this is good. I know we always have lots of data struggles of getting the data. We might not always have it. So what if we don't necessarily have to have data that's exactly the same or similar as the thing that we're going to be working with? well, apparently it's good enough just to go get a very diverse set of other kind of somewhat related things just in them being data sets. But if they're diverse, that's okay, it will do just as well. So the authors conclude, and they basically mention that again, this is a graph-centric foundation model for relational databases. It's really interesting because it unifies this kind of single table and cross-table embedding so we can share information effectively. It handles mixed data, which is actually very tricky to do in practice with graph neural networks. And it significantly outperforms all other existing methods, so that's great as well. So that's the work. I guess moving into my critical review of this work now, I guess my first question then would be like, what about if we don't have a good column names? Because we might be able to think back and remember that when we were performing our cross attention, I think it was the keys were the column names of the things that we were working with, but they were transformed into vectors first. So the question I'm asking here is basically like, all of this is being done under the assumption that these names are kind of like good or that they're nice. So we might think about like users, and one of the column names might be like username or user ID, and these things might be like easily embedded into this space. But what happens when they're not so nice? What happens when it's like a 0, or what happens when it's some long kind of key or random value? What would happen in that case? And then again, I'm always thinking about the time complexity. That's not really reported in the work, so I think that would be good to see like, hey, maybe this Griffin module is awesome, but it takes 1,000 years to run, versus if you just take the mean, this thing will run in 2 seconds, even if it has a lot of error. So yeah, that would be good to know. Also, in terms of critical review, how much work is being done by the sentence embedding? It seems like a lot is being done here, right? Because that's the thing that's actually creating the initial representations for the table metadata, as well as the column metadata, as well as any kind of categorical or textual feature in the database itself. Maybe this is also an expensive operation to just always be performing, who knows? So that's something to be mindful of. I guess another last kind of critical question I have is like, why aren't different sentence encoders used? It seems like one of the most central parts of the work, so why wouldn't you see something like glove or another sentence encoder I talked about 2 weeks ago called all mini LM, the whole name? So why not use different ones? So that basically forms my critical review. In terms of personal review, what happens if you change the subgraph masking mechanism? So what happens if you don't just go after like the temporal domain? What happens if you like all other parts of the temporal domain? What happens if you only get the last like 2 days? What happens if you get the last 2 weeks? What happens to performance as you might change that? Also, what happens if you like increase the fan out parameter? Instead of considering 20 samples, maybe you consider 100. What happens there? So that's those are all questions that I would have. It would be interesting to understand the performance as a function of the database size as well. We can go back and see that some of the databases that they have had like 20 tables, or they had like 100 columns in some of them. So if we only trained on like really small databases, like, and then we just started to perform inference on this really large database, would that still work? Would be one of my questions. A couple others would be typically ReLU is used as the activation function. I also went and checked, and in the original Attention is All You Need paper, they don't use this Xiyuan, they use ReLU, so that's kind of interesting. I'd want to know some more justification. They don't really give it. And then what about other types of data? So here they're just kind of considering text data, maybe as categories like cat, dog, bird. They might also be considering numerical data that they can perform regression on. But what about like images or videos or graphs or audio or all these things that we might be able to just say, hey, here's this data structure, we're going to put it in this cell of the table. Maybe that would be really good if you're thinking about things like Twitter where there's lots of images. Maybe having some kind of embedding for that could also be beneficial. So, and then maybe also combining that with other tasks like segmentation somehow, I'm not sure, but maybe that's possible. So yeah, that forms my review kind of the paper. Here's some of my references, and I would just like to thank everyone so much for listening to this paper. Thanks.